Okay, so beginning of this chapter, polynomial functions, power functions, but now we really want to get into polynomial functions more, solving them, graphing them. And so we're going to spend a couple days on this and a couple days on 2.4, and then we're going to have our test for chapter 2, part 1. Then we'll have a second half for chapter 2, part 2. So first of all, really important idea that a polynomial function of degree n has at most n minus 1 local extrema points. That means turning points, max and mins, and at most n zeros. And so think about one that we hopefully feel pretty good about, y equals x squared. A quadratic graph only has one turn in it, right? 1 less than 2. And it has at most 2 zeros. That's the most times it can cross. It can cross less times. And so sometimes you can tell from a graph, right, like just based on this, if it turns 2 times, that means that it's at least a degree 3, which means it could cross the x-axis 3 times. And so finding those zeros, the degree becomes really important. Okay? So the first one here says, describe how to transform the graph of x cubed into 2 times x minus 3 cubed, and then sketch the graph and the given y-intercept. And so, first of all, if you just graph y equals x cubed, think about what happens with that graph. That's an odd function. When you plug in 0, you get 0. When you plug in 1, you get 1. When you plug in 2, though, 2 to the third is 8. And so this graph goes up really quickly, right? So this is like the parent graph, y equals x cubed, one of the graphs we learned about in chapter 1. And so if I graph this really quick just as the background, remember that this goes up. It starts just at 1, 1. But at 2, it goes to 8. And think about at 3, it goes to 27. So it goes up very, very quickly. And because it's an odd function, when you pick the negative x's, you get the negative y's, right? So it turns like this. And then at negative 2, it's all the way down at negative 8, right? So it has that little twist in it. So you can just pick points here again. But I hope maybe that we're using the transformations to help us a little bit. Minus 3 means that it's shifted to the right. To the left. No, to the right 3. I was right the first time. Because if I plug 3 in there now, I get 2 times 0, which is 0. So I'm just shifting this over 3. But by multiplying it by 2, I'm stretching it, which means if I pick right next to it, instead of just going up 1, I'm going to go up 2, right? So it's going to go up like this. And if I pick the negative, it's going to go down to negative 2. And think about if you pick the next point, 5 minus 3 is 2 to the third, which is 8 times 2, which is 16, which means it's going to go up even at a faster rate than the original graph because it's stretched. And if you stretch an x cubed graph enough, it's going to stretch out and look like a straight line. That little twist isn't as obvious. Domain and range of this, all real numbers, because both arrows are pointing up. One's pointing up, one's pointing down. The y-intercept, how do you find the y-intercept of a graph? The y-intercept is when x equals 0, right? So on the original, the y-intercept is just 0 because it crosses at 0, 0. But look at my red graph. What's the y-intercept on this? Well, how do I find the y-intercept? I want to solve for y, right? G of x is the same as y. But I'm going to plug in 0 for x. That's a definition of a y-intercept when x equals 0. And think about what the y-intercept of this would be. It would be 2 times negative 3 to the third, which is negative 27. So the y-intercept on here wouldn't be until negative 54, and that's because it's going down so quickly. And so y-intercepts sometimes are very helpful to graph, but sometimes they're not because who wants to graph that, right? I think maybe this should have been covered up on your paper, but that's okay. Leading coefficient test. To determine which way the arrows go on your graph, you can use the leading coefficient, which is the degree. N is the degree, right? And then the leading coefficient is the number in front of that highest degree. And so when your degree is odd, remember that your arrows are going to go in opposite directions. And if you need me to do a little dance for you, I can do that in class. Remind me. But when the degree is odd, your arrows are always going to go in opposite directions. If the leading coefficient is positive, like y equals x cubed, what's going to happen? Well, the positive, like if this is your graph, the positive side's going to go up, and the negative side's going to go down with whatever happening in the middle. How do we write that? We say as x goes to infinity, f of x, or y, also goes to infinity. And as x goes to negative infinity, the y is pointing down, the left side's pointing down, which is negative infinity. Okay? Maybe some vague memories of this. But what happens when the leading coefficient is negative? Like y equals negative x to the third. Well, think about that. That's a reflection over the x-axis. So now the left side's going to flip up, and the right side's going to flip down. I always remember when it's positive, positive stays with positive infinity, negative stays with negative infinity, and then it flips on this, right? So now if I go to positive infinity, what's happening to my y? Well, now it's pointing down, so it goes to negative infinity. And as x goes to negative infinity, the left side of my graph is now pointing up, so it's going to positive infinity. All right, this is called the in behavior of your graph. So look, this was supposed to be covered up. That's what these boxes are for. Even functions, right? Even functions, the arrows go in the same direction. Think about x squared, right? Y equals x squared. We know what that looks like. Both arrows point up. But for any even degree function, both arrows are going to point up. So if the leading coefficient's positive, both arrows go to infinity. So that means as x goes to infinity, f of x also goes to infinity. And even when x goes to negative infinity, the left side of my graph, as x is getting smaller, what's happening to the y? It's still pointing up. So it's still going to infinity. So remember, this is the only part that changes on each one of these, right? The way you write this, what happens to as x gets really big, y goes to what? What happens as x gets really small, y goes to what? Okay? And for a negative leading coefficient on an even function, again, think about y equals negative x squared. What do we know? We know both arrows point down. So now these are just going to change to negative infinity. So as x goes to infinity, f of x goes to negative infinity. And if x goes to negative infinity, f of x goes to negative infinity. So if I ask you for the in behavior, I want you to write it out mathematically. But graphing it, it's important to know this because it helps us know what the graph looks like. Other really important things to know, if you have x to a power, right, where n is an integer, which means polynomial, no fractions, no decimals, no negative exponents. If n is an even degree, right, we know that's going to touch the x-axis. And again, relate it to what you know. Y equals x squared, we know, comes and looks like this. It doesn't cross the x-axis, it touches it. But if n is odd, like y equals x to the third, what do we know? We know that it actually crosses at that 0. All right? And so, again, helpful when we're graphing really big polynomials to know that even degrees touch and odd degrees cross. So today, look at these equations. They're already factored for us. Find the zeros. The zeros are the x-intercepts. They're the solutions. So when it's already factored for us and we're trying to find the zeros, all you do is say what each of these go to 0, right? What makes this go to 0? X equals 1. What makes this go to 0? X equals negative 2. And what makes this go to 0? X equals negative 3. I could even say each one of these crosses the x-axis because the exponent out here is just a 1, right? And so I even know they're going to cross the x-axis at that point. What about the in behavior? The in behavior, I need the degree, so be really careful on this. If I multiply x times x times x, I get x to the third. That's odd. That's a positive leading coefficient. So what do I know about the in behavior? I know odd functions go in opposite directions. So the left side goes down, the positive side goes up. So I'm going to say as x gets bigger, y gets bigger, and this is how we say that. As x goes to infinity, y goes to infinity. And what happens to the left side of my graph? As x gets smaller, y also gets smaller. Okay? If it asks for the in behavior, you can't just draw the arrows. So what about this one? Zeros, set each one equal to 0. So 2x plus 1 equals 0. So if I subtract 1 and divide by 2, there's a 0 at negative 1/2. And this one, even though it's x minus 4 to the third, if you set that equal to 0, if you take the cube root of both sides, right, the cube root of 0 is still 0. So don't let that cube out there change the fact that it's still going to be 4 that makes that go to 0. We'll talk about tomorrow what that does to the graph, what being a cube, but it still has a 0 at 4. Now, in behavior, be really careful, right? I'm not going to work all this out because that's a lot of work, but I know this is 2x, and if I take this and I write it out 3 times, that's really x to the third. So what's going to be my biggest degree when I multiply those together is going to be 2x to the fourth. So now that's an even degree function with a positive leading coefficient, so I know that both arrows are going to point up. So to write that out, I'm going to say as x goes to infinity, f of x goes to infinity. And even when x gets smaller, because it's x to the fourth, it's still going to point up to positive infinity. Okay? What's my time at? 11 minutes. Okay. So describe the end behavior, and what else do I have here? Find the zeros of the function. So describe the end behavior on this for me. I'm going to put them in as questions so that you can practice doing that. And then on this one, find the zeros, which means what if it's not factored for us? Can you factor that to find the zeros? We'll do those in class.